Welcome back, everybody. In this video, we'll be doing one more example from section 4.1 that involves making up an exponential function and answering a question about it. And then we'll be going on to section 4.2. So let's go ahead and get started with the example. So this one is number 63 from our textbook. It says in the year 1985, a house was valued at $110,000. I'm not sure where that is. It says by the year 2005, the value had gone up to $145,000. We want to know the annual growth rate between 1985 and 2005. And then assume that the value continued to grow by the same percentage. We want to know the value of the house by the year 2010. So one thing that we can do is, to help simplify our calculations actually, is instead of using the years here, 1985 and so forth, we're going to do everything starting with 1985 as year 0, and then do all the other years relative to that. So what I mean by that is this. So we're going to make a little table. We're going to show the year. I want to set a value of t for that, and then the house value. Okay. And so in 1985, we'll make that our year 0. The value of the house was 110,000. Okay. And then in 2005, that'll be 20 years later, right? The value of the house is 145,000. Okay, and then by the year 2010, which would be year 25, we don't know that value, and we're going to try to come up with a formula we can use to figure out what that value would be. All right, so the formula for an exponential function is going to be f of t. I'm using t for time here instead of x for x. Okay, so f of t is a b to the t power. And so we have basically 2 points on the graph, and we're going to use those to help us resolve what a and b are. And then once we have the function, we'll be able to answer the question about 2010. Okay, so let's take 0 first. So f of 0, that's 1985. That will be a b to the 0 power. B to the 0 is going to be 1. So this will equal a, and we know that has to be 110,000. Okay, so we know a is 110,000. So what we've got now is f of t is 110,000 b to the t power. So we've used up everything we can from that first data point from 1985. Now we're going on to 2005. So that's year 20. We know that the value is 145,000. So f of 20 will be 110,000 b to the 20th, and that's supposed to equal 145,000. Okay, so this gives us an equation in B that we're going to be able to solve. So let's do that right now. So we have 110,000 b to the 20th power equals 145,000. Let's divide both sides by the 110,000. Okay, so here that's the same as 145 over 110. That simplifies stuff just a little. I could keep going and divide out the 5s as well, but there's no need. So we would need to get the b by itself. Right now, b is 145 110ths, and it's b to the 20th. So how we're going to do that is we're going to raise it to a power. And what we're going to use is a rule for exponents that says if you have, let's use different letters, x raised to the m power, and then that's raised to the n power, then you should have x raised to the m times n power. For example, 2 cubed raised to the 5th power would be 2 to the 15th power. We're going to use that exponent rule. And so right now, b is raised to the 20th power. We're going to raise that to the 1/20th power because 20 times 1/20th is going to equal just 1. This is, notice it's going to end up being the same as taking the 20th root of b to the 20th. Okay, of course, we'll have to do that to the right side as well. So we'll have 145 over 110 raised to the 1/20th power. And so we'll have just plain b on the left side. And then the right side is 145 over 110 raised to the 1/20th power. And then let me get a number for you out of the calculator. Okay, and that's 1.0139. Okay, and that is going to be our base, okay, for our exponential function. So we have our a and our b, so we're ready to write down our complete function at this point. So f of t will be 110,000 times 1.0139 raised to the t power. So there's our complete function. As far as the growth rate, taking a look inside the parentheses, it's 1.0139, so it's 1.39%. That's going to be the annual growth rate. Okay. And then lastly, we want to know the value in the year 2010. That's just going to be a plug-in. We'll find f of 25. So f of 25 is 110,000, 1.0139 to the 25th power. So it should be more, it will be more. $155,336. Okay, all right, so that takes us to the end of that example. We've read through the problem, and basically we were given 2 points, okay, a t and a value, and we use that to construct our exponential function, and then we use that exponential function to answer a question. All right, so I actually wanted to add a little bit more to this house example that we just finished. I went ahead and made the graph for our function, and it looks like that. The scale here is like 0 to 30. Remember, that's years basically since 1985. The vertical axis runs from about 110,000 to 200,000 for the upper limit. Because the scales are so different and the growth rate on the function is so low, it's only 1.39% per year, the line or the curve looks almost straight. But if you zoom out on it, it does exhibit more of that characteristic kind of exponential function shape. So changing the axis scaling can really dramatically affect what the graph looks like. Again, I wanted to point out that this thing ends up as an exponential function because the growth is assumed to be nonlinear, okay? We're assuming that the growth is going to be exponential. We could have run this problem as if the growth were linear, that is, that it added a constant dollar amount at each year. But here, we're doing it as an exponential function. So we could have reworked this as a linear function. We would have gotten a different answer, okay? All right, so that's finally the end of this example. We'll be going on to section 4.2 next. All right, sorry, just a little bit more about the house thing. I decided to go ahead and figure out what would happen if the growth was linear after all. And so here's how it goes. You take and calculate the slope by taking the change in value, so that's 145,000 minus 110,000, divided by the change in years, which was 20 years, and that works out to be 1,750 a year. And so the point where it was 1985 turns out to be our y-intercept. So our f of t this time is 1750 times t plus 110,000. So there it is a linear function in slope-intercept form. And then calculating the value for the house after the 25 years, we get 153,750, which isn't too far off of what we got before. It's about $2,000 difference. And then I went ahead and graphed both right next to each other. And you can see over the kind of smallish time frame that we're considering, just 20, 25 years, that the two functions are not that far apart, and which is why after 25 years, the two estimates for the value are pretty close. Of course, if you go further out, again, if you zoom out, there's going to be a more obvious difference between the exponential function and the linear function. Okay, so which one's right? Well, it depends on which way you think the growth is going to go. A lot of times, real phenomena have more of an exponential type growth. Things like the rate of inflation and values and salaries and things like that tend to grow more of in an exponential way rather than a linear way. Often we use a linear function because they're easier to work with, but an exponential function can be a little bit more accurate. All right, so that's the end of the example, I promise. Now we will really go on to section 4.2. All right, so here's section 4.2. 4.2 is a shorter section. It's about really the graphs of exponential functions. And so the first thing I wanted to do here was to revisit the graphs of 2 to the x and 1/2 to the x. So 2 to the x first. So remember that for this, the base is constant. So the base on this is going to be 2. Yeah, there's our function. F of x is 2 to the x power. And so the base is constant and the exponent changes. For 0, when x is 0, 2 to the 0 power is 1. So the point 0, 1 is on the graph. 2 to the first power is 2. So the point 1, 2 is on the graph. When you raise 2 to powers bigger than 1, you get bigger and bigger answers, which is why the graph just goes up and up and up. If you raise 2 to negative powers, you get answers less than 1, which is why the values all kind of hug the x-axis going towards the left. The x-axis is a horizontal asymptote for the graph of 2 to the x. It turns out that all of the functions where the base is bigger than 1 have that. Sorry, it's disappearing on me. There it goes again. Let's try that again. Okay. All of the functions b to the x where the b is bigger than 1 kind of have that property where they're increasing. Functions like that are used to represent things like that house problem. Sorry, I said it was going away. And growth of money using compound interest and things of that sort, things that increase bacterial populations over time and whatnot. Okay, here's a graph of 1/2 to the x power. This time it is a base that is less than 1. And that's not coming up well. Okay, and so for this one, every time we are raising 1/2 to a power that is less than 1 or less than 0, we get values bigger than 1, which is why the graph is increasing up to the left. For values that are bigger than 1, we're raising 1/2 to bigger and bigger powers, which is why we get answers that are smaller and smaller and smaller. Okay, raising 1/2 to the 0 power, you'll get 1. Raising 1/2 to the first power, you'll get 1/2. So those 2 points are going to be on the graph. And once again, the x-axis will make a horizontal asymptote for the graph of our function. It turns out that all of the functions b to the x, where b is in between 0 and 1, have that kind of, it's doing it again, that kind of characteristic property that they're increasing or decreasing over time, rather. So the exponential functions kind of divide into two subfamilies, the increasing kind and the decreasing kind. All right, so here's some kind of general information about exponential functions. This kind of ties together some of the things that I just said. So they're all one-to-one. These functions are all one-to-one. They have a horizontal asymptote. The line y equals 0 will be their asymptote. The domain is all real numbers on all these. The range 0 to infinity, unless you've shifted it in some way. There's no x-intercept. They do come down and like hug the x-axis because it's an asymptote, right? But they don't actually cross the x-axis, again, unless you've shifted it or something. Y-intercept is 0, 1. And they're increasing if the base is bigger than 1 and decreasing if the base is less than 1. Okay, so you should get to know the information in the table here. Okay. All right, so let's see a couple of examples. So here's a whole bunch of exponential function graphs. And you can see that the way the graphs are shaped really depends on the size of the base. For all of the functions where the base is bigger than 1, they're all increasing. So taking a look, you'll see the graph of 2 to the x. I'm in red. Let's zoom out a little bit. The graph of 2 to the x here in red is increasing 3 to the x, 5 to the x, and 10 to the x, and so on, right? So those are all increasing. And also you'll notice that the bigger the base is, the more quick the growth is. And that's kind of characteristic of all these, where the base is larger than 1. Also, you notice that they all pass through the point 0, 1, because any base raised to the 0 power is going to equal 1. So they're all going to pass through this point, even the ones where the base is less than 1. Okay, so all the ones where the base is less than 1 are decreasing. Again, they pass through the point 0, 1 and are decreasing. Another thing that you'll notice is the ordering of the functions. On the functions that have a base that is bigger than 1, you'll notice that it is 2, then 3, then 5, then 10 for the bases. In terms of the colors, it's red, black, blue, and purple, and then going from bottom to top. But the ordering is reversed on the other side of 0. It's purple, blue, black, red. So where they grow faster on the right side of 0, it looks like they drop off towards 0 more slowly on the other side of 0. And you'll see that happen with the bases that are smaller than 1 as well, that they kind of switch the ordering as they pass through 0. Okay. Just so you know, you don't have to be able to draw these graphs really, really well by hand. That is, how could you see very easily the difference between 2 to the x and 2.3 to the x, right? You do want to kind of know the qualitative differences between the graphs. That is, are they increasing or are they decreasing? The important points they pass through, and so forth. Okay. All right, so we're going to try to do a couple of graphs here. So here it says let f of x equal 1/3 to the x. We're going to graph f of x. We'll label 2 important points on the graph, and then also we're going to state the domain and range in interval notation. So let's go for the important points first. So I know that f of 0 is equal to 1. So the point 0, 1 will be on the graph. Okay, and then also 1, f of 1 is 1/3. So the point 1, 1/3 will be on the graph. Okay, we could plot a couple of other points as well. So -1 will give us 3. And then -2 will give 9. All right, and sure enough, there's one of those decreasing exponential graphs. So we'll label our 2 important points as 0, 1, and then 1, 1/3. And then we needed to state the domain and range. So let's do that. So the domain is all real numbers. That should be easy points. The range here is going to be 0 to infinity. All right, so there's one example when decreasing function. Okay, so we're going to have another one next. This one is going to involve a translation. All right, so in this example, we want to graph 2 raised to the x minus 1 power plus 3. So we want to do this in terms of translation. So let's just remember what the graph of 2 to the x looks like. It's increasing because the base is more than 1. It passes through the point 0, 1, and 1, 2. That would be the 2 to the x function. In the exponent, we have not x, but x minus 1. That's going to be a right shift by 1 unit. And then the plus 3 will be up 3. Okay, so the vertical shift will be 3. So that means that rather than having the x-axis for a horizontal asymptote, it'll have the line y equal 3 as a horizontal asymptote. Okay, and then the way that I would draw the rest of this is just think about how the important points would have to have moved. We know that on our regular 2 to the x graph, it passes through the points 0, 1, and 1, 2. So I'm going to take that point 0, 1 and move it right 1 and up 1, 2, 3 units. The point 1, 2, we'll take that point and move it right 1 and up 1, 2, 3 units. Okay, so there's those two kind of important points. So let's go ahead and draw the graph. You can put more careful into it if you want to. All right, but that's basically our graph. We've shifted it. Shouldn't go under its asymptote like that, sorry. Okay, all right, so that basically is how that graph plays out. Again, the way that I would approach this overall is to figure out what the kind of non-translated graph looks like we did 2 to the x, figure out where its important stuff is, like where's the asymptote, where's those two important points, and then figure out what shifts had to have happened. In this case, it was a right shift by 1 and an up shift by 3, and then move those important features, like we moved the asymptote up 3, and we moved the two important points right 1 and then up 3. And then we just sketch the graph. Okay. All right, so the last thing that I wanted to do out of this section was really compare the growth rates for x squared and 2 to the x. Because the two functions, in a way, in terms of their formulas, kind of look alike, right? They both have an x and a 2. One is x squared, one is 2 to the x. And if you draw their graphs, especially if you do it by hand, they start looking like that, right? Just kind of starting at the origin almost, and then kind of growing up to the right. I want to think about how quickly they actually grow. Of course, the parabola graph passes through 0, 0, where the exponential graph passes through 0, 1. They both will pass through the point 2, 4, and then they both just kind of go up from there. So I wanted to really kind of look further at how those graphs actually will go. So to do that, we're going to do kind of a thought experiment and think, okay, well, here's the graph on the horizontal axis. On your screen, it's some size. I can't know how big it is, but let's say we were going to draw this thing on paper, and we're going to draw it in such a way that 1 is going to be 1 inch on your paper. So you're going to need to get a big piece of poster board or something. So when you go to the right by 1 to draw the graph, that's going to be 1 inch actually on your paper. And then vertically, of course, will be the same. If you go up 1, it's going to equal 1 inch. Okay, and then let's say that we're going to draw the graphs of x squared and 2 to the x, the two graphs that we're trying to compare. And we want to go to the right and put the graph, for x equal 20 on the graph. Okay, when we go to the right to x equal 20, and then we have to go up, I want to see how far up we're going to have to go to plot that point. Okay, so let's start with x squared. Okay, so when x is 20, we'll have f of 20, and that's 20 squared, or 400. That's 400 inches. And so let me turn that into feet for you. Okay, that is like about 33 feet. That's 33 1/3 feet. So that's really big, right? And if you think about it, that makes sense because you're squaring a number, it's going to be really big. So if you go get your piece of poster board, if you go to the right by 20 inches to draw this point for x equal 20, you're going to have to go up by 33 feet. So you have to get up on the roof, right, to draw that point. All right, so now let's see how it looks for 2 to the x. Okay, g of x is 2 to the x. So that will be g of 20, and that's 2 to the 20th power. Okay, so 2 to the 20th power is 1048576, and that's in inches. So let me turn that into feet. That's 87,381 feet, or about 16.5 miles. Okay. All right, so that's interesting, I think. So just a little movement 20 inches to the right, on your paper, your poster board to draw this graph. For the x squared graph, you would have to get up on your roof, a little past that, right, 33 feet up, okay. But for the 2 to the x graph, it's 16 miles. And there's a big difference between 33 feet and 16 miles. And so if you think about it, that's huge, right? Just moving to the right by 20 inches. The y change in one is going to be like 33 feet. The y change in the other is like 16 miles. I wanted to point that out because if you just look at the graphs, like it's shown on the screen here, it looks like they do almost the same thing, right? I know that down here at the origin, they act a little differently, and then they cross at the point 24, and then they just kind of go up from there. But they don't really go to the same place, right? They're both head off towards infinity, but at drastically different rates. And the exponential function grows much more quickly. All right, so that takes us actually to the end of section 4.2. We're going to be looking in the next section, 4.3, at logarithm functions, which are the inverses of the exponential functions. Okay, in the meantime, let me know if you have any questions, and have a great day.